Did you know the search for extraterrestrial intelligent civilizations is real? Frank Drake developed an equation to explore the possibility of life beyond our world.
Let's take a look at the Drake equation and explore the search for extraterrestrial life. This is STEM in 30.
Hi, I'm Marty.
And I'm Beth, and today we're going to talk all about little green men.
No, we're not. Today we're going to talk about the Drake equation. It is pretty complex, but don't worry, it's pretty straightforward algebra.
In 1960, astronomer Frank Drake conducted a pioneering search for interstellar radio signals.
This was a several-week-long effort called Project Ozma, named after the queen of L. Frank Baum's imaginary Land of Oz, a place very far away, difficult to reach, and populated by strange and exotic beings. The object of the Ozma experiment was to search for signs of life in distant planetary systems. This experiment attracted a great deal of attention, and an informal gathering of accomplished researchers and engineers was assembled to discuss the possibilities of finding such a signal. Frank Drake developed his equation in 1961 in order to stimulate conversation at the first scientific meeting on the search for extraterrestrial intelligence. The equation is used to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way Galaxy. While the Drake equation has not led to scientific proof of extraterrestrials, one of its more famous uses was by Star Trek creator Gene Roddenberry. He cited the Drake equation in his proposal for Star Trek to support the idea of having numerous inhabited planets. However, not having committed the equation to memory, and remember, this was in pre-internet days, so he couldn't just Google it, Roddenberry was forced to invent his own. When the Drake equation was developed, our technology only allowed us to observe stars in the Milky Way Galaxy. But today's technology allows us to distinguish individual stars beyond our own galaxy.
As we mentioned earlier, the Drake equation is just algebra.
A big, scary-looking algebra problem. But it's really not that different from what you do in class.
To help us explain algebra, we talked to our friend and former math teacher, Joe Acaba.
He's not in the classroom anymore, but he's still got a pretty cool job. He's an astronaut. We are joined by NASA astronaut Joe Acaba, a veteran of 3 space flights. He spent over 300 days in space, and he was a teacher before becoming an astronaut. Joe, thanks for joining us.
My pleasure. Thanks for having me.
Joe, you taught math and science.
Yes.
I was not very good at algebra, but I think we have a demo that may have helped me. Marty, do you have some equations?
We're going to have 1g equals xc. The g stands for a glue stick. And the C stands for a paperclip, the X being our variable we don't know. So we're going to try to balance this equation now. So Joe, can you help us out a little bit?
I will.
1.
We need more than that.
2, 3, 4, 5, 6, 7, 8, we're getting there. Oh, we're starting to one more.
11.
The pressure's on.
12.
And it looks like we're
good. All
balanced.
right.
So now we know that 1g equals 12c. 1 glue stick equals 12 paper clips. Now let's make that a little bit harder.
Go ahead and put that with a glue
With
stick.
the glue?
Yeah.
All right.
So now we have that 1g, the glue stick, plus 1p, the pen, equals 12 paper clips. We already know that that equals the glue stick. Now we're going to have to add in more paper clips. So that's our xc. So let's add a few more paper clips
Okay.
here.
All right.
1, 2, 3, 4, 5, 6, 7.
8. There we go.
And we're balanced. And so an algebraic equation is just balancing each side of it. So now we know that 1g plus 1p equals 12c plus 8c. We've got 20 paper clips over here equaling these. And if we do a little bit of math and subtract, we have to take the same thing off of each side. So if we take the glue stick off of that side,
See ya.
Now we're unbalanced. So we know that the glue stick equals 12 paper clips. So we have to take 12 paper clips off of this side. And now we see that our equation is balanced once again.
So, Joe, when I was in middle school, all I needed to know was that I just had to keep both sides balanced.
They always have to be balanced. Life's got to be balanced, and math's got to be balanced.
And that's why math is such an important part of a balanced education.
Right on, there you go.
Let's take a closer look at the Drake equation.
It's big and scary, but like we learned from Joe Acaba, we just need to balance both sides.
Solving one side gives us an answer that balances out the other side.
One of the things you will notice on the Drake equation is that the variables look different from variables you've seen before.
In a math textbook, an equation might have an x or a y to represent an unknown number. You often solve for the unknown value.
In the Drake equation, letters and subscripts are used to represent unknown quantities. So don't get intimidated because our first variable looks like this. It's just a different way of representing an unknown number. In the Drake equation, n will be our answer. In today's episode, we're going to take a look at each of those variables a lot closer and learn what they mean. At the end of the episode, we're going to put our best guesses in and see what the answer could be.
Here's the great thing about the Drake equation. There are no right or wrong answers yet, because right now, these are all guesses at their best.
Let's head over to Goddard Space Flight Center to learn more about the rate of star formation, the first variable in our equation.
The sky is full of stars. If we've ever had a chance to go out on a dark night or in a dark place, you can see stars sometimes from horizon to horizon. But what many people don't realize is that stars come and go over long periods of time, and stars are still forming. They form when some of the gas that exists between stars in our galaxy and in other galaxies begins to collapse into little clumps under its own gravitational pull. And if there's enough material, that clump will be highly pressurized, eventually igniting what we call fusion in the core of that little clump. That means the atoms fuse together and produce light. So that's what we see as starlight. Scientists are studying that process of star formation. We can see these regions in the galaxy where stars have recently turned on, and their bright light is illuminating the remaining gas in the cloud out of which they form. We see that in these beautiful, colorful nebulae that we see with the Hubble Space Telescope and now with the new Webb Space Telescope. We can begin to study the rate that stars are forming. How many form every day or every year or every century? That's a hard problem to solve. We can look at distant galaxies and look at some of this radiation that comes from young stars and the regions in which they are born, and we can measure how bright that radiation is. That tells us something about how quickly stars were forming in the distant universe, which means kind of the distant past, because it's taken time for the light to get to us. And we can compare that with the rate of star formation in our own Milky Way galaxy. Now, some of those stars are bigger than our sun, and some of them are about the same size, and a lot of them are smaller than our sun. But what kind of stars? Some stars are not suitable for having planets and life around them. We kind of need to know the rate at which the stars that are sort of like our sun, or that might be able to have habitable planets, is forming. And we come to the conclusion that that's about 2 or 3 per year.
One variable down, a lot more to go.
Next up is F subscript P, or F sub P, which stands for the fraction of stars with planets.
When Drake first developed the equation, our technology was limited and we were only able to search within our own galaxy.
New technologies have greatly expanded the search for planets beyond our solar system and even our own galaxy.
When scientists turned the Hubble Space Telescope to look deep into an area of space we thought was mostly empty, the image it sent back was of thousands of galaxies.
each with their own stars and planets.
And more potential F sub Ps than Drake and his colleagues could have imagined.
The James Webb Space Telescope is going to greatly expand our search for exoplanets.
Something else that's very exciting, which is if you point JWST at nearby stars, there is a good chance that if these stars harbor planets, that Webb will be able to detect those. If nature cooperates, and we're very lucky, there are opportunities potentially that we can detect atmospheres on these planets. And once you can detect atmospheres, a whole new field of interesting things can open up.
To help us learn a bit more about the search for exoplanets, let's head over to astronomy educator Shauna Edson.
I hear you all want to learn something about how we find exoplanets. Great. Well, I'm going to show you using this model. Now, if one of you can hit that switch to start our planets. Stars, like this light bulb, make light and they shine it in all directions. But if you can see the little planets around it here, the planets aren't making their own light. They're just reflecting the light that the star shines on them. If this is a star somewhere in the sky, if I point a telescope at that star and I'm looking for these little exoplanets, can I see the planets? Most of the time, no, right? They're too faint, they're too small, they get lost in the light of their star. So we can't see the exoplanets directly, but we can figure out that they're there using something that we can see, which is the star's light. Now that's what this is doing. This is a light sensor. It's looking at that light bulb star and it's measuring how much light it sees. I'm going to start the measurement. So on this screen, this is how much light our light sensor is seeing. Now what is happening to the brightness of that star? It's shifting. So what is causing the light to drop, or it to look like the star is getting less bright?
Planets blocking it?
Exactly. Every time one of those little exoplanets goes in front of the star, it blocks a little bit of the light, just like you might do with your hand blocking the sun. If we can't see this part in our telescope, if all we get is the measure of that brightness, we can still figure out a lot about those exoplanets. So just from this, we can tell how big the planet is. What is it on the graph that tells you how big the planet is?
How long the dip is?
Exactly, how much light it blocks. A bigger planet is going to block more light. It's going to make a big change in the star's brightness. A smaller planet is only going to block a little bit of light.
Finding planets beyond our solar system is just the first step.
We'll also have to determine if they could sustain life.
And it's not that easy. It can't be too cold.
It can't be too hot.
It has to be just right.
We inhabit a little blue planet called Earth. Earth is habitable because it had the right conditions and ingredients to enable life as we know it to evolve and flourish. And one of the most important factors in making our blue planet habitable is the wet stuff itself, water. It's kind of extremely important for life. When it comes to the search for habitable exoplanets, planets outside our solar system, we think the ability to have liquid water on a planet's surface is just as important for those worlds. There's a handy concept astronomers use to help them figure out where to look around any given star for exoplanets that just might have the right stuff for life. It's called the habitable zone. It's the distance from a star where a rocky planet with an atmosphere could have liquid water on its surface. In our solar system, the habitable zone extends from around the orbit of Venus to around the orbit of Mars. Earth happens to be nice and comfy in the middle. But it takes more than just a good location. Orbiting in the habitable zone does not guarantee a planet will be habitable. After all, the moon is right here with us, but it's certainly not habitable. Sorry, Moon. The location of the habitable zone depends on how big and bright a star is. The nearest star to our sun, Proxima Centauri, has at least one planet in the habitable zone. But because Proxima is much smaller and dimmer than our sun, its habitable zone is way smaller and closer to the star. So every star has a habitable zone, but that doesn't mean there will be planets there. For example, the star known as Kepler-90 is similar to our sun, and it too has 8 planets. But they're all huddled super close to the star, well inside of the habitable zone. But the longer we look, the more likely it becomes that one day we'll find another little blue, water-covered planet right in its own comfy habitable zone. And that would be a planet worth a closer look indeed.
Before we get to the next variable in the Drake equation, we need to talk about sample size.
I love M&Ms. So if I reach into this bag and I pull out a blue one,
that gives us a sample size of 1. So I can assume that all of those M&Ms are blue.
Are all M&Ms blue?
Not quite. As a matter of fact, if you sort out a bag of M&Ms, you will see that there are a variety of colors.
And if you sort more than one bag, or even 2 or 3 bags, you get a larger sample size and a better representation of what the colors of M&Ms are.
The same goes for the search for life beyond our planet.
The rest of the variables we're going to talk about have a very limited sample size of 1, Earth.
Which is why it is important to study planets beyond Earth. Here is postdoctoral fellow Dr. Mariah Baker on why we study Mars.
One of the reasons that we really want to study Mars is because we know that Mars at one point in the past looked a lot more like Earth than it does today. So understanding why it changed, how did the climate change on Mars so much over the last couple billion years, really helps us kind of get at those questions about habitability and understanding solar system and planetary formation as a whole. I think that we often think that we sort of understand everything about planets, but before we ventured off into the solar system, Earth was one data point that we had. And so increasing our understanding of different planetary environments and geology on different planets, it helps us get kind of a more comprehensive understanding of these long-term processes that are guiding planetary evolution and that help us understand where life could exist.
Which leads us to our next question. What is life?
We know life on Earth has looked like this, and this, and this, and this, and even this.
And today, life looks like a lot of different things, from plants to animals to insects.
While the thought of aliens and little green men running around is interesting, and we see it all the time in science fiction, we haven't even found single-celled life on other planets. Yet.
But what if we don't find life on Mars?
I think that we will continue the search. Humans tend to enjoy exploring the solar system and figuring out our place in the universe. And to answer those kind of big questions about whether or not we are alone and whether Earth is really unique, we need to continue searching for signs of life.
And that brings us back to the next variable in the Drake equation, F sub L, which is the fraction of planets that actually develop life. Right now, we only know of 1, and that's ours.
What fraction of planets do you think could or has developed life? Think about it. Stick around until the end, where we will give you our best educated guesses for that variable and all of the others.
Moving on to the next variable, we're looking not just at life, but intelligent life.
The dictionary definition for intelligent life is beings that can learn and understand things.
And we have a whole lot of examples of that from right here on planet Earth. Some alligators put sticks on their heads to attract birds looking for nesting materials.
Some crows have been known to use tools.
Beth's cats have learned to open doors.
And Marty's dog will do just about anything for a treat. These all fall into the definition of intelligent life.
We aren't quite there to detect this type of intelligent life on other planets.
Imagine that Earth was inhabited only by giraffes. We would have a planet full of intelligent life, but no way for them to signal any other planets.
That's where the next variable comes in. F sub C is the fraction of planets that develop intelligent life that are capable of interstellar radio communication.
Think of our sample size of 1, Earth. We have interstellar radio communication now, but think about all the time before that.
When modes of communication were not as high-tech, like letter writing, signal flags, or even just talking to your neighbor over the fence.
On Earth, We have giant radio telescopes set up to detect radio signals.
They study a lot of different things, including stars, galaxies, and quasars. And they're used for SETI, or the Search for Extraterrestrial Intelligence.
Marty had a chance to visit the VLA, or the Very Large Array in New Mexico, to learn more about these types of telescopes.
I'm joined by Lorraine Bowman. Thank you so much for talking with us today.
Thank you.
Now tell us, what is a radio observatory?
A radio observatory is a lot of radio telescopes all electronically linked together, and we like to look at the universe at different frequencies than our normal eyes do. So a radio observatory looks at the universe and the radio frequencies. While the VLA does do some solar system stuff, we look at the sun and planets a little bit, but for the most part we look a lot at galaxies near and far, and we look at regions within galaxies like star-forming regions, supernova remnants, all types of things. So what the telescopes are actually doing is they're collecting photons or waves, just like optical telescopes do, or even our eyes. Our eyes actually collect optical photons. These telescopes are basically bigger eyes, and they work at a different frequency, but overall it's kind of the same mechanism. So we're collecting radio photons or radio waves, and because the radio waves are physically bigger than optical waves, which is why we want bigger telescopes. But then we get this electronic signal, which we can all combine. We can combine together the signal from all the dishes together, and then we can actually get images or maps of the region of the sky the telescopes were pointing at.
And as a matter of fact, we're quite a ways away from the dishes right now, and that's for a very specific reason, something that just came up yesterday, right?
Yeah, so just yesterday we had a fast radio burst emission, which we don't really understand what they are, but they are what we call targets of opportunity, so we want to study them as soon as they pop up, for as long as we can. And the VLA is really good for this because those radio bursts come to us with a sort of delay, so when you hear about the observation, we can try to point and look and try to observe this thing.
Hang with us. We have one more variable to get through. Then the fun math starts.
L is the number of years that an intelligent civilization remains detectable.
Basically, we're looking at the lifespan of civilizations. Again, our only sample comes from Earth and from archaeologists who study ancient civilizations. Our next guest is an archaeologist, but he studies the Earth from space.
Hi, my name is Timothy Murtha. I'm a professor here at the University of Florida in the Center for Latin American Studies and the Florida Institute for Built Environment Resilience. In my research, I'm an archaeologist and an anthropologist, and we study the material remains of culture. In particular, I'm interested in how ancient cities developed and evolved through time, and how we can study those by using remote sensing, or images that are taken from space, so that we can map how ancient cities impacted their environments. We also use all sorts of technology to just help us do traditional archaeology so that we can get a better understanding of how many people there were and how long those civilizations last. Remote sensing is using images that are taken from drones, planes, and outer space to capture pictures of the planet at particular periods in time and using particular sensors. These images then can be processed so that you can highlight particular features on the landscape. We use the remote sensing now prior to going into the field to inform where we start to sample. So we still go out and we still use traditional survey methods, but now we can be more precise about where we look and how we go about those measurements. How long do civilizations last? I think if I were to answer this question 30, 40 years ago, I might have come up with a number that has actually been put forward for the Drake equation, something like 300 to 400 years. Because if you look at most civilizations, the peak of those civilizations is relatively short. So the Aztec Empire, for example, was really only 200 years in its full length. The classic period of the Maya is 800 years. And they estimated that civilizations last about 300 to 400 years. But here's the tricky side to that equation. When a civilization collapses, or when a civilization's political system collapses, the information and the knowledge from that civilization continues on. And so calculating the length of time a civilization lasts on the planet isn't as simple as looking at the earliest date and the latest date. Sometimes we have to factor in that the knowledge from that civilization is transformed and replaced by another civilization that's nearby, or it's one that has evolved and changed and may look a little different and may have a different name, but lasts another 300 or 400 years. And I think it actually gets to the heart of why I am an archaeologist, because I am convinced that there is information that is still yet to be gathered from these civilizations that will help us as a civilization today moving forward.
Woo! We made it through the whole equation.
But keep in mind that the Drake equation was developed only for our galaxy. But now we have a lot more information about a lot of other galaxies.
We've learned about the rate of star formation,
stars with planetary systems,
what life is,
what planets might not only have life, but intelligent life,
the ability to communicate beyond their planet.
We've looked at how long these civilizations might last.
And that leads us back to N.
N is the number of intelligent civilizations broadcasting their presence to the universe.
Like us.
We've asked an expert to help us plug in some of those numbers.
Hello, my name is Will Armentrout. I'm an astronomer here at the Green Bank Observatory. I study star formation across the Milky Way, mostly with radio telescopes. And right outside my window, about 200 feet away, I can see the room that Frank Drake and Carl Sagan and the Order of the Dolphin talked about the Drake equation for the very first time back in the 1960s. So the Drake equation is something that allows us to estimate very, very roughly how many civilizations might be in our galaxy that we could potentially communicate with. And then we have all these other factors that help us to make this estimate. And the first one is our star, the rate of formation of stars suitable for the development of intelligent life. This one we can study with astronomy. For my estimate for this number, I'm going to say about 3 stars per year. The next term in the Drake equation is F sub p, the fraction of those stars with planetary systems. Pretty much every star out there in the Milky Way has planets around it. So if every star has planets around it, then F sub p would be about 1. So the next one, N sub e, is the number of planets per planetary system with an environment that is suitable for life. But it doesn't look like most stars necessarily have planets like that. So I might put a value of 0.1. So that's basically saying, okay, maybe 10% of stars have a planet around them that could sustain life. The next number, F sub L, the fraction of suitable planets on which life actually appears, we only have one data point here, and that's the Earth. But if we were to detect life on another planet or a moon somewhere in the solar system, then I think that that would be good evidence that this number is pretty high. And so I'm going to be really optimistic here and say that F sub L should be about 1. The next term in the Drake equation, F sub I, is the fraction of life-bearing planets on which intelligent life emerges. And I think that's probably a little bit rarer than life itself. So I might put a value of 0.1 for F sub I. So that's saying that maybe 10% of planets that have life on them eventually develop intelligent life. The next fraction, F sub C, is once you have intelligent life, how many of those intelligent civilizations are going to develop technology that releases into space detectable signs of their existence. And so I'm also going to say that F sub C should be pretty high, and I'm going to give this a value of 1. L, I think, is the most uncertain. So L here is the length of time such civilizations release detectable signals into space. At that first SETI meeting here in Green Bank, they said that L could be somewhere between a couple tens of thousand years to 100 million years. So let's say that L is equal to 100 million. And so if I plug all of those numbers in together.
Now we have all of our numbers and we just needed to solve for N.
This is a good chance for you to pause the video, take out a paper and pencil, or maybe a calculator, and plug in the numbers. See what answer you get. Unpause when you're ready. Do you think we can unpause yet?
I think so. They seem like a pretty smart bunch.
And our answer is
about 3 million. And so that says to me that there might be about 3 million intelligent communicating civilizations just in our Milky Way. This is a nice thought experiment that you can use not just for the Milky Way, but all throughout the universe. And it really gets you to think about how big the universe is. And even if there are a lot of communicating civilizations out there, I think we're still probably, it's still probably pretty special to make life. And so we should take care of ourselves so that we get to that 100 million year lifetime or even beyond.
Did you get the same thing? Now it's your turn.
go back through each of the variables and plug in your best guess. Do the math and see what your answer is.
The most pessimistic predictions point to Earth being the only place where all of these criteria have been met.
The most optimistic predictions right now put the number of radio communicating civilizations in the billions, with a B, billions.
Let us know what your prediction is down in the comments.
And if you enjoyed today's episode, be sure to follow STEM in 30 on Facebook and Twitter, and subscribe to the National Air and Space Museum's YouTube channel.
Who knows, maybe you will be the person to answer the question, are we alone?
Thanks for watching.